Alright, so this screencast will focus on what are called buffered solutions, and it would be my strong suggestion that if you haven't already read through this section in your textbook, to go ahead and stop the screencast and do that. There's a lot of vocabulary and just conceptual understanding. In light of that, the College Board has kind of tamed down the math that's involved with these buffer solutions. It used to be some pretty multi-step calculations where they tested you over buffers, but they've kind of taken that away and simplified it quite a bit. But they really hit the conceptual understanding pretty hard, so it's important that you be able to explain what a buffer is, predict if a mixture of two different solutions would form a buffer, and then to know what part of the buffer would respond to acid and base stresses. So again, if you've not already gone through and read, please do that. So a buffer in general contains a weak acid or a weak base and its conjugate, which sounds pretty simple, and it is. So you've got to know your weak acids, or basically know your strong acids, and then everything else is a weak acid. And then when you're looking for the weak base, the conjugate acid or the conjugate base, know that they're going to give it to you probably in a salt. So like the first example is HF. HF is your weak acid. NaF, we don't really so much care about the Na, but we know that when this is put in water, it breaks up into Na plus and F minus. So F minus is the thing that we care about. That's going to be the conjugate base, and so that would form a buffer. NH3, ammonia, which is a weak base. NH4 plus and Cl doesn't look like there's anything in common, but we know that NH3, being a base, picks up a proton and forms the NH4 plus. So that would be a buffer as well. So the thing that makes buffers cool is that you have both an acid and a base present. So I like to think of it as both of them, like, of course, turning them like into people. They're not people. But you've got these two things that are sitting in the beaker, ready and waiting to deal with stresses. So like in the case of this first buffer, the HF and the NaF, if we were to add a base to that buffer, the HF is the one that's sitting there ready to deal with it, because an acid can neutralize a base. If I stress the buffer with an acid instead, this acid is not going to be able to do anything with that H plus stress. But the F minus will be able to, because since he's the conjugate of a weak acid, he is a good base, and he can take on the H plus and then form a sink basically for that, and neutralize the acid. So we'll run through the math of this first one, practice 3. This goes just like the section that we just did, so I'm going to run through it pretty quickly. It talks about, let's see, grab my pen. It's not happy with me today. There we go. Alrighty. So it says formic acid. Again, don't stress, it's just a different name. That's a 1-carbon carboxylic acid, so methanoic acid is another name for it. Gives you the starting concentration, it gives you a Ka, and then it tells you it's mixed with sodium formate. And so we don't really care about the sodium because that's a spectator, but this guy, since it's a salt, will break up into Na plus and COOH minus. So here's our common ion, right? So when I write out my equilibrium, we've got HCOOH breaking up into H plus HCOO minus. I'm actually going to write that differently. I'm going to write it like this, so that way you're not confused. Alright, so there's our common ion, there's our weak acid, so we definitely do have a buffer here. I'm going to put in the initial concentration, so 0.250 molar and 0.100 molar. This is 0. At equilibrium, this will go down by x, up by x, up by x, and again, just what we saw in the last section, so I'm going to kind of fly through this. So that K is small enough that we're going to assume this is 0.250 and this is 0.100 and call it a day. So 1.8 times 10 to the negative 4. Again, avoid putting x squared because it's not x squared. 0.100 times x over 0.250. X is equal to our H plus, and that comes out to 4.5 times 10 to the negative fourth molar. So to get our pH, minus the log of that, and it comes out to 3.3. Should have another sig fig there, but I don't have it handy. So anyway, we've got kind of a starting pH, and you always want to stop and ask yourself, is that a reasonable pH? We have a weak acid mixed with a conjugate base. That pH better be less than 7. If you get something greater than 7, you know you've messed something up. Alright, so here's what we're going to do to this buffer. We're going to stress it. I guess we're not going to stress it. That's interesting. Okay, so I picked a totally... Maybe we stress it down here. Okay, we do. I'm not losing my mind too much. Okay, so this kind of takes a break from that example problem. So it says a buffer composed of NH3 and NH4 plus. NH3 is our weak base. NH4 plus is our conjugate acid of NH3. So it says when HCl is added to this buffer, the NH3 soaks up the acid's proton, forming NH4 plus. Because that proton is now locked up in the ammonium ion, it doesn't serve to significantly change the pH. So it's really a matter of neutralizing that H plus, and it's really going to resist the change in pH. So the reaction would be H plus plus NH3 forms NH4 plus. And it is a single reaction, not a single reaction, but a one direction reaction, because as long as there's enough NH3 there, it's going to absorb all that H plus and just form the conjugate. Now, the opposite case, if I stress this buffer with OH minus, that ammonia is not going to do anything to neutralize OH, right? Because these are both bases. But what we have present in the buffer is the NH4 plus. And what it can do is donate that proton, right, to the hydroxide, which it will, and just form H2O and NH3 plus. So instead of that pH dropping dramatically because of adding that strong base, it'll only go up a little bit because you're forming some of that NH3, which is basic, which will drive the pH up. But it's much better than having just those free hydroxides. Alright, so in practice 4, this is what I was getting at, they ask you to reference practice 3. So remember that system was HCOOH, and then we had sodium formate, which we don't care about the Na, we care about that present. So I find it helpful to label what they are. So this is a weak acid, and then the COOH minus is the conjugate base. Because this is just Bronsted-Lowry theory, right? Acids are proton donors, bases are proton acceptors. That's all it is, and that's all buffers are. But students get really confused about who's going to deal with what. So I want you to picture this weak acid sitting in the beaker and the conjugate base sitting in the beaker. If I throw an acidic stress, so if I were to add protons, the acid can't do anything about it as far as resisting pH changes, but this base certainly can, right? So this says use the same buffered system and write the reaction that would take place. Well, the weak acid is not going to do anything with it, but the conjugate base of that weak acid is going to be able to do what with that H plus? Well, he's just going to pop it on, and that'll be a sink for the H plus. So yes, we're generating an acid, and yes, the pH will drop a little bit, but it's not going to be the huge dramatic change we would see if we just added the H plus by itself, assuming that we were adding H plus to water. Alright, so same buffered system. Now we're stressing it with OH. Well, the conjugate base can't do anything to neutralize OH, because they're both bases. A base can't neutralize a base. But you've got the weak acid sitting there. So you say to yourself, okay, well the weak acid is going to do what acids do. So HCOOH is going to donate a proton to OH, and it'll form water and COOH minus. So again, we're creating that conjugate, the pH might go up a little bit because that is a conjugate base, but nothing again compared to that OH minus. So that's kind of the conceptual side of how you deal with buffers. Now we're going to deal with the math by using something called the Henderson-Hasselbalch Equation, which also makes me think of David Hasselhoff every single time I hear it. Has nothing to do with Knight Rider or David Hasselhoff. Sometimes you'll see it as the h squared equation, and it's really helpful, but it does have something called pKa in it. And so I don't want you to stress, because if you think back to when you first learned about pH, I told you that mathematically, anytime you see a little p in front of anything, it just means negative log. So all pKa means is we're going to take the negative log of the Ka. So there's your formula right there. And basically it turns these kind of nasty little numbers, right, that are written in scientific notation, into nicer numbers. So it asks you to calculate the pKa of chlorous acid. So the Ka is given, so all we have to do is negative log the Ka, and the negative log of 1.2 times 10 to the negative 2. We know we should get a number around 2, right, because a log just undoes the base 10. And we get 1.92. So it's a much nicer number to say that the pKa of chlorous acid is 1.92 rather than saying that the Ka is this. But both are useful and it doesn't really matter which you're given. Alright, so the pKa for nitrous acid, again, negative log of the Ka, so 4.0 times 10 to the negative 4th. When I do that, I get 3.40. So again, remember we got a new sig fig rule for our logs. This has two significant figures, so the thing you're taking the log of, its significant figures should match the number of decimal places. So that's why I've given it 2 decimal places. Alright, and again, 3.4 is pretty close to 4, and 1.92 is pretty close to 2. So those are reasonable numbers. Alright, so here's the Henderson-Hasselbalch equation. So it's nice because it basically eliminates that first ice table that we've been doing. So in the first section and then the very first problem we did in the screencast. So instead of doing the ice table, you can plug into this formula. Now, of course, if you forget this formula, you can always do an ice table, but it does save you some time if you can remember it. It is important that you remember it's B over A. Feel free to remember Bridget Adkins, right? So it goes in that order, but the base has to go on top. And that this is a Ka. If we want to use it for base problems, we've got to do a little work, but it's really worth it. So we will be using it when we do our bases. Alright, so for this practice problem, they tell you we have lactic acid. They've given you the chemical formula. They've given you a Ka, so we know that's a weak acid. And then sodium lactate is an ionic compound. And so in water, it's going to break up into Na plus and C3H5O3 minus. Again, doesn't matter if you've never seen lactate before, right? You see that sodium, you know it's ionic, you know it's soluble, it's going to break up. And then hopefully you notice, oh, I've got this lactate, and that's a common ion for this acid, right? So again, instead of going through this whole ice table, I know that the concentration of my acid was given to be 0.75 molar, and the concentration of my salt, which I don't care about the sodium, I care about the lactate ion, so the concentration of my C3H5O3 minus is 0.25 molar. Alright, so this is my acid, this is my base. Again, I think it helps to label it so you don't screw something up later. So to get the pH, we do the negative log of the Ka, 1.4 times 10 to the negative 4, plus the log. The base is going to go on top. Base, 0.25. Acid, 0.75. pH equals, so I've got 3.85 when I do this log, and then plus a negative 0.48. So the pH is 3.37. Before you stop and say, oh, good job, I got the answer, ask yourself, is it reasonable? We've got an acid, pH should be less than 7. Our pH is less than 7.